Thank you for your attention. My name is Masahide Sasaki from NICT, and I would like to express my sincere gratitude to all the participants for joining us here today at the conference on Updating Quantum Cryptography and Communication 2015. The purpose of this half-day conference is to present our latest achievements and our new challenges on quantum cryptography and communications. So it consists of 5 parts. Part 1, Introduction and Reminiscences. Part 2, Fiber Network. Part 3, Space Network. And Part 4, Next Challenges. And Part 5, Relay Talk and Discussion. So let us start Part 1 with a dialogue between 2 founders of this field, Dr. Charles Bennett and Professor Jules Brassard. So I'm delighted to invite Charlie and Jill on the stage.
Good morning. So, Masahide has asked us to reminisce about our first meeting and how this field was created.
This is a meeting that we had in the ocean, as Gilles is about to explain.
Yeah. So the way that this really started, it sounds unusual, but it's a true story. It was in November 1979. And I was swimming in San Juan, Puerto Rico, minding my own business, when a complete stranger swims up to me. And without any provocation on my part, starts telling me that he knows how to use quantum mechanics to make banknotes, money, that is impossible to counterfeit. So I politely listened to him, and by the time we swam back ashore, we had our first paper written. And yeah.
So what I told him about was some ideas that I'd heard of some time earlier from a college classmate of mine, Stephen Wiesner. And he explained these ideas to me back in 1970. And this, in retrospect, may have been the first mention of the term quantum information theory. It's yes. So this is my transcription of his ideas. He wanted to use quantum effects to send 2 messages in one package, such that the receiver could read either one, but in receiving one message would destroy the other. His initial idea of how to do this turned out to be wrong, and that's why I marked it false. But it turned out to be the seed of another important discovery in quantum communication. However, he had another idea which was easier to understand, and that's what I explained to Gilles Brassard. Oh, here is the guy. Yes, I should say. And this is what he looked like back in those days. And this paper described the quantum banknotes. This paper he tried to get published in IEEE, submitted around 1970, but it didn't get published until 1983. So here is the idea, the quantum banknote. There. Oh, come on. Should be next. There. Why is this forward is no? Oh, it. Yeah. There we go. Whoop.
No, go back.
There we go. Yeah. There it is. So a quantum banknote has 20 quantum systems. Oops. Yes, 20 quantum systems in it, and the idea is that if you try to observe any of them, you'll disturb them with some probability, and therefore it cannot be copied by a counterfeiter who doesn't know what these quantum systems are. I'll now give this over to Gilles.
So we realized, we worked on these ideas for a few years after meeting in the ocean, and then we realized that we were using photons represented here to store, that this was following Wiesner's original idea, that we were using photons to store quantum information, But everybody knows that photons are meant to transmit information, not to store it. And then when we thought of using these ideas to transmit information, that was the seed to transmitting secret messages and the real birth of quantum cryptography. So we wrote a first paper in 1982. This was the first time that we thought of using quantum information to send an actual secret message. And the paper was submitted to one of the major computer science theoretical conference called STOCK in '82, and it was rejected. And it was only published last year, 32 years later, in Natural Computing. So if you thought that Wiesner's paper, written in 1970 and published in 1983, was pretty bad, in our case, it was 32 years before we published. But the reason why we didn't publish earlier is that we kind of gave up on this when we discovered what is known as BB84, which was a much more practical protocol for quantum cryptography. And this one we submitted and got published in IEEE International Symposium on Information Theory, but in 1983. But there was only a one-page abstract for each paper. So all we could do is announce the result without giving the protocol. So the first time the protocol was actually printed was in a conference in Bangalore, India in 1984. That's why it's called BB84, even though it's a 1983 discovery. And then we had this is the original 1983, where we described the idea known as BB84 for quantum key distribution, which is well known. But it was also something else in the same paper, which is less known.
And this was an, oh, wait. I should leave you with this. So there we go, yes. So a lesser known part of this 1983 and 1984 papers was the getting back toward the idea of sending a message in such a way that you couldn't change your mind about it later, and that's what we proposed here was a quantum protocol for doing it, and then a way of defeating it by a quantum effect called entanglement. And this is possibly the first intentional use of entanglement in information processing. Then, of course...
And then our ideas, or our theoretical ideas, which were sound, were not appreciated. In fact, the only reason that this paper was published in 1984 is that it was invited. I was invited to present anything I wanted, so I thought it was a good idea to present something that was rejected everywhere. And so nobody took us seriously, which is nice because we didn't take us seriously either. But at some point it became annoying, and we decided to build the first apparatus, a proof of concept, just to show them that it's not nuts. So this is the first apparatus that we built in 1989, and it worked for the first time to the day on the 10th anniversary of our meeting in the ocean. So it was published in Scientific American with Arthur Eckert as co-author.
And so now, I mentioned entanglement before. Now, David Deutsch was the pioneer of quantum computing, and one of his papers had a cryptic reference to quantum cryptography that you could hardly notice. What did I ask this? Oh, there we go. I'm so sorry. Okay, yes. A cryptic reference down here that is that something entangled state could be used for performing quantum cryptography as opposed to defeating something. So this idea was developed, or I think maybe independently discovered and carried on to great effect by, there, I did it, Arthur Eckert. And this is his paper, which pointed out that using entanglement, you could get quantum cryptography by a violation of Bell's inequality. And this made it both more widely appreciated and also gave rise to a brand of quantum cryptography which is in some sense stronger, which you may hear about later in the conference, in which you don't need to trust the manufacturers of your equipment. this is important in cryptography, that you shouldn't have to trust the people that you buy your equipment from.
All right. I think we should stop. And well, thank you for your attention. So this is about the first 10 years of quantum cryptography.
Yes, it got much more complicated after that.
Yeah, when it got out of our hands. Thank you.
You.